Hi and welcome to this Applied Maths video. Today we're looking at difference equations and specifically second order homogeneous difference equations. So in this video, we're going to explore second order difference equations to understand that a little bit better, specifically homogeneous, and then we're going to solve second order homogeneous difference equations. So just to let you know, the video here is suitable for all applied math students. So we're going to be looking at both ordinary level and higher level examples. We'll go through ordinary level and easier examples first, and then the higher level are at the end of the video. You can use the chapters below to skip to the question, the higher level question, if that's what you prefer. So this is video 2 of 3 on our difference equation series. The other 2 videos are linked in the description below. So when we're solving second order difference equations, the first thing we need to be able to do is identify them. And I spoke about this in the previous videos. Because we have 3 different types of difference equations and all have a different method of solving, the most important thing we have to do is to first of all understand, well, what type do we have? So a second order difference equation is a recurrence relation where each term in the sequence is defined as a linear combination of 2 preceding terms and no constant or independent term appears. So basically it's going to look like this in blue. So a Tn, I'll just underline this. So we're talking a Tn equals b Tn minus 1 plus c Tn minus 2. Now, just like when we talked about our first order, with second order, it doesn't necessarily have to have 3 terms. What a second order needs in order to be second order is a difference of 2 between the terms. So what we mean by that is the biggest term here will be our Tn. Our other one is going to be Tn minus 2, and the jump between that is 2. So that's what makes it second order. So even if this term wasn't there, it is still a second order. So don't fall into the trap of thinking 2 terms, it's first order, 3 terms, it's second order. That is in general going to help us, but it may catch you out if we're missing one of the terms. So as long as we have a difference in 2 between the terms, so they're not the first term and the second term, it would have to be like the first term and the third term. Once we have that, then we have our second order. And that's going to be true for both homogeneous and non-homogeneous. So I'm talking about second order in general. So what's key about our second orders is we can create what's called a characteristic equation. And that is basically taking our difference equation and creating an algebraic quadratic equation based on it. Here we can see the connection. So the biggest term, our Tn, becomes the x squared. Any coefficient stays the coefficient. Our next term, so that's Tn minus 1, becomes the x. Notice that coefficient staying as well. And then our last term, so in this case Tn minus 2, becomes the constant. So notice how it has no x. Okay, so there's 3 pieces here, and we can see that it creates a quadratic trinomial. Now, as I was saying earlier, if this piece was no longer there, that is still a quadratic equation. We just have to use difference of 2 squares to solve that. So that's what we mean by focusing on the difference between the terms being 2 rather than there just being 3 terms. Because just like a quadratic, we can have a quadratic binomial, but more likely we'll see a quadratic trinomial. So all the exam questions we've seen to date, and remember we haven't a huge amount. So at this point in time, we have for higher level a sample paper. We have 2023. We have a 2023 deferred paper. We have 2024. At the time of recording, we don't even have a 2024 deferred paper. So as of now, we have always had 3 pieces when we're talking about second order, but just to be aware that that may not always be the case. So here are the steps to solve a second order homogeneous difference equation. And one thing that you'll find as you get towards the end of your applied maths course and when you start to bring in a bit more revision and going back over things, often in our topics, the process is going to be the same regardless of our question. So we can really think of these step-by-steps as the way to answer any question. And difference equations in general can be tricky because every question could be about a different topic. So, one could be about salmon, another could be about turtles, and another could be about population. We'll see one later about jewelry. And we can see loads of interest rate questions. So you can do savings and debt, but all the steps to solve them are going to be the same. And that's important. So here are our steps to solve a second order homogeneous. So the first thing we're going to do is find the characteristic quadratic equation. So that's taking our difference equation and converting it into a quadratic. The second step is to solve the quadratic. Okay, so those two steps are relatively straightforward. You can solve using factorization, which is usually the quickest. You can use your minus b if the numbers aren't particularly nice. Step 3 is we're going to use the difference equation theorem 1 or 2 depending on the roots. So you don't need to know the proof of this theorem. This is just something we're going to use. If you'd like to know more about the proof, you can look into that. But for now, we're just going to focus on using these two theorems. And the two theorems are the difference root theorem. So imagine we have the roots alpha and beta, and that's a bit of a callback to the old maths course. So Tn is equal to L alpha to the power of n plus m beta to the power of n. If you use different letters, that's absolutely fine. The letters mean very little here. We're going to be looking for numbers to put in instead of those letters. I like to use alpha and beta for the roots, and L and M makes sense then to pop in front, but you can call those letters anything. So if you learn them in a different way, that's perfect. So this works when you have two different roots, alpha and beta. Now, if we have a double root, so if we get our two answers and they're both the same, so if that quadratic was a perfect square, we only have one root effectively, and that is alpha. It is a double root, so it is there twice, but it's the same. So if we subbed it into this, we're going to end up with alpha here as well, and effectively our end result will just give us one part. So what we end up having to do is it's very similar. We have L alpha to the power of n plus m n alpha to the power of n. Okay, so we have a little n in here that doesn't appear in the line above. Other than that, it is going to be the same. So far, we haven't seen any double roots. The double roots are a little bit easier to work with because the alphas are the same. Instead of getting a simultaneous equation, we end up with a slightly easier version where we figure out L and then we can figure out M separately. So they work out as two linear rather than having to work them in like the traditional simultaneous equation way. So step 4 is going to be sub in two values of n and solve simultaneous equations for L and M. So in a second order, you'll see that you're always given two terms. So you might be given like T0 and T1. Okay, and we need that because without that information, we wouldn't have enough information to solve for our L and our M. And then step 3, write down the solution for Tn. If you've already reviewed your first order, you'll know that actually we rarely use Tn. It's going to be another letter, P for population, or it could be any letter at all that tends to make sense. We've seen a lot of P's, we've seen some U's, and just like that there. So whatever your solution is for Tn. So it's quite a straightforward process, and most students prefer this even over the first order. So we're going to do some straightforward questions first, and then we'll look at some exam questions. So here's an example where we're just solving a second order homogeneous difference equation, and they give us U0, U1, and then they said evaluate U8, the nth term. Okay, so I'm going to do this kind of our step by step. So step 1 is to write the characteristic quadratic equation. So this is my x squared, this is my x, and this is my constant. So that creates x squared, because there's no coefficient, minus 2x, because it is a coefficient of minus 2, and then minus 3 equals 0. So that's your first step. You're writing down that quadratic. The second step is then to solve that. So you can solve that whatever way you want. I'm going to use factorization because it's nice and quick. And then we end up with x equals 3 and x equals minus 1. With numbers like this, like you shouldn't really be going to minus b. However, if you are kind of in a different question and it's a little bit trickier, absolutely, if it speeds you up, use your minus b. So the third step then is we're going to figure out which of our two theorems we're going to use. And because we have two different roots, we're going to use this formula here. So the formula is Tn equals L alpha to the power of n plus m beta to the power of n, where this root here is going to be my alpha and this root here is going to be my beta. If you did this the other way around and your alpha and beta were mixed up, then your L and M will be different, but effectively we'll get the same answer. So your L will be my M and vice versa. So don't panic about the right way to label your roots. As long as one is alpha and one is beta, that's absolutely fine. So what that creates then is U is what we're using here in this question, L 3 to the power of n plus m minus 1 to the power of n. So just a quick note on filling in your roots. You should have a bracket around the root and the power n outside. This is especially important for negatives. So minus 1, if that n was written inside, you're going to end up with your incorrect sign on your answer. So if you did minus 1 to the power of 2, you would technically be doing 1 to the power of 2 and then making a negative. So it's really important that you get good with writing this in the correct way. So step 4 is then we're going to sub in two values and do some simultaneous equations. So what that means is we're going to take our U0 first, right? I'm not putting in equals here because each line should only have one equals. So I'm going to sub in everywhere there was an n. So think about this. So there's my n, my n, my n. I've changed that to 0. So anywhere there was an n, I'm now putting in my 0. So I have 3 to the power of 0 plus m minus 1 to the power of 0. Okay, we can see that here. And we were told in this question that U0 equals 1. So I'm going to let this equal 1. Be careful and really get clear on what we're doing here, because often students have an idea but it's not clear enough. So I see a lot of equal zeros. So make sure you're clear. We're subbing in n is 0 and our answer should be 1. Anything to the power of 0 is 1. So this leaves us with the equation L plus M equals 1. And that is equation 1. Okay, we're going to do that again. And this time we're going to use the second bit of information we were given, which is U1 equals 11. So this gives us U1 L 3 to the power of 1 plus m minus 1 to the power of 1, and that should all equal 11. Again, you're focusing on putting in that number 1 instead of your n, so into those powers. So we'll tidy this up and we get 3l minus 1 to the power of 1 is still minus 1, so this is minus m, and that equals 11. And that is equation 2. So we're going to solve these. This is still the same step. So we're going to pull these together. So I have L plus M equals 1. 3L minus M equals 11. That gives us 4L equals 12 and L equals 3. So then going back to equation 1, we can say L3 plus M must equal 1. So then m must equal our minus 2. So then the final step is going back over here and pulling that un and subbing in the numbers we've got. So that gives us 3 to the power of n plus, well, it's plus minus, so we'll go straight to a minus 2 minus 1 to the power of n. And I've just put that in the wrong place. So that's our final answer. So we have solved the second order homogeneous difference equation. So what I didn't speak about earlier, but we talked about it quite a bit in our first order video, it's what we mean when we say solve. So what we're doing is we're releasing the dependency on the previous terms. So the formula we were given at the start of this question, so un plus 2 minus 2 un plus 1 minus 3 un equals 0, allows us to do a little bit of work, but only if we know the previous terms. When we solve difference equations and any difference equation, what we're doing is we're releasing that dependency on previous terms. We're writing, in this case, our UN just in terms of n. And what that allows us to do is to calculate U 1,000, U 1,000,000, U 150,798. So rather than going through each step, we can go to very big terms quite quickly. So now that we have our answer, we're going to answer part 2, which has asked us to get U8. So that's going to be a calculation where we plug in, instead of our n, we're plugging in 8, and we go to our calculator. So just make sure you have your brackets in the right place. That can often cause problems. I know it sounds very basic, but these are things that tend to go wrong. So we end up with 19,681 for our 8th term. So now let's look at a second order homogeneous difference equation question. Here we have Tn plus 1 minus 8Tn plus Tn minus 1 equals 0. They give us T0 equals 1 and T1 equals 12. So let's go through this step by step again. So step 1 is to write our characteristic quadratic equation, which in this case is x squared minus x plus 16 equals 0. Step 2 is to solve that equation. So we get x minus 4, x minus 4. And you could see that this is actually a perfect square, meaning we only get one answer. So when we get to step 3, we're going to be using the double root theorem. So that is just one root. So we're going to be using Tn equals L alpha to the power of n plus m n alpha to the power of n. So what that's going to look like for us is Tn equals L 4 to the power of n plus m n 4 to the power of n. So then step 4, you're going to see it gets a little bit easier when we end up using this theorem, the double root theorem. And just be careful, we're looking for L and m. N is not an unknown. N will depend on which term we're working with. So this n is not an unknown we're looking to solve. So just bear that in mind. So the two bits of information that we've been given in this question, T0 equals 1 and T1 equals 12. So we're going to set up our equation. We're going to set up T0 first. Again, 1 equals per line, so don't write equals because then you'll get confused. So this is T0. I'm simply labeling it. It is L 4 to the power of 0 plus M 0 4 to the power of 0, and that should all equal 1. What happens here, and what makes this a little bit easier, because we get T0 generally, this part is going to disappear completely because we're multiplying it by a 0. So that is gone, leaving us with L times 4 to the power of 0, which is just 1. So we get L equals 1. So then we don't get an equation like we did in the last example. We actually get our answer straight out. So this is why it's a little bit easier. Technically, it's still simultaneous equations. We still need to work with two equations, but we're not doing our traditional method of solving them. So now let's do T1. We have L 4 to the power of 1 plus M 1 4 to the power of 1. And that all equals 12. But remember, we also know what L is, so we can sub in our 1 here, that's 4, plus 4m equals 12. We have 4 plus 4m equals 12. We have 4m equals 8, and m equals 2. So we can do this much quicker. And like I said, up to now, up to October 2024, we haven't seen any questions that require us to use the double root theorem in any of the exams. So now, final answer. So this is step 5. Final answer, Tn equals, our L is 1, 4 to the power of n plus m, which is 2, and 4 to the power of n. Now, what you can do here to tidy up that a little bit is get rid of that 1 because we don't need it. So 1 is not doing anything, plus 2n 4 to the power of n. And you can see here that if this n wasn't there, effectively we'd be able to add those two parts together and we'd have too simple an answer. So bear that in mind as a way to remember kind of the fact we have a different theorem for our double root, especially if you're practicing exam questions and you don't see this a lot. So example 3, we're going to jump straight into an ordinary level question. This is from the 2024 paper. It is question 10, part A. A small local jewellery business started selling their products online on January 1st, 2024. They sold 9 pieces of jewellery in January, 12 pieces in February. With a marketing plan, the business predicts a strong growth in online sales. They predict that J, the number of such jewellery pieces sold in any month, will be equal to the number of pieces sold the previous month plus twice the number of pieces sold the month before that. This prediction can be expressed as a second order difference equation, and they give us the equation here. So basically all of this information is contained right here. Okay, so that big paragraph of work for us at ordinary level, it's going to generally be given to us. So it's good to read through it, but it's not going to be really, really important information. They then told us n is greater than or equal to 0, n is an integer, and they gave us J0 and J12. They even gave us the corresponding characteristic quadratic equation for this. You don't even have to make it. Okay, so lovely and straightforward. So the first thing they're asking us to do is to solve this equation. So let's work with that. So that's going to be x minus 2, x plus 1 equals 0, and that gives us two roots, x equals 2 and x equals minus 1. So now they ask us to hence or otherwise solve the difference equation. Now the thing is, right, this was step 1 of our steps. This is step 2. So this question, we're going straight into step 3 if you're following the step-by-step process of how to solve our second order homogeneous difference equations. So we have 2 different roots, and that means we're using the different root theorem, which is going to be, in this case, Jn equals L alpha to the power of n plus m alpha beta to the power of n. So that's our theorem there. So then when we fill that in, we get Jn equals L 2 to the power of n plus m minus 1 to the power of n. Again, don't worry if your alpha and beta are mixed up. That's absolutely fine. You're just going to get my value of L as your value of m and vice versa. Okay, so now that we have done that, we're going to take some information and plug it in. So we're going to start with J0. So that gives us L 2 to the power of 0 plus m minus 1 to the power of 0, and that should all equal 9. So I'm going back to my question up here. So that gives me L plus m equals 9, and that is effectively this is equation 1 that we're going to work with. So then we go and do the same thing again. This time for J1, we get L 2 to the power of 1 plus m 2 to the power, minus 1 to the power of 1, and that should all equal 12. So 2L minus m equals 12, and that is effectively equation 2. So if we pull those two equation parts together, we get L plus m equals 9. We get 2L minus m equals 12. That gives us 3L equals 21, which gives us L equals 7. And then if L plus m equals 9, but L is 7, then m must be 2. So that gets us our 2 bits of information. And our final answer is going to be Jn equals L, so 7, 2 to the power of n, plus m, which is 2 minus 1 to the power of n. And that's our final answer for part 2. So then the next part asks us to calculate the number of pieces of jewellery that the model predicts will sell in July, which is month 6 of trading online. So that means we're dealing with J6. Now that was very nice of them to say because July is the 7th month. But we're talking about starting here in January, which is our J0. So that's why this July is like our 6th month. So just be careful with that. But they were very clear in the question. Most students wouldn't even think to question it. They would just go straight into the idea it's month 6. Okay, so we plug this into our calculators. And we end up with, on this one, power of 6, make sure those ends and powers are outside your brackets, and it predicts that it will sell 450 pieces of jewellery. So this is an ordinary level question. We're going to see a higher level question next. And the ordinary level questions are really good to practice, even if you're going to do higher level, because it gets you in the process. What happens with the higher level questions is they might have a little bit of a trick to them, but generally it's going to be the same process. It's just our numbers are going to be slightly, I'm going to say harder, but really it's more awkward. They're going to be awkward numbers. They're going to be decimals. They're going to be fractions. It's going to take a little bit more thinking. That's really how they step this question up from being an ordinary level question to being a higher level question. So example 4, we're going to look at a higher level question, and it's from the 2024 paper, and it's question 9. We're only going to look at parts 1 to 3, and that's because the rest of this question was a non-homogeneous second order difference equation. So we're going to look at that in the next video. So remember, this is video 2 of a 3-video series on difference equations. The other videos are linked in the description below. So we will look at how the second order non-homogeneous are asked, and we'll bring in how that links to the second order homogeneous that we're covering now. My advice to you is to try all the ordinary level questions. They only look at second order homogeneous, and make sure you're very comfortable with that before you start looking at the homogeneous questions that bring these both together. So a geologist is carrying out a survey of an opal mine. During the first month of mining, a mass of 200 kg of opal was removed. During the second month of mining, a mass of 245 kg of opal was removed. The geologist predicts that M, the mass of opal removed in any month, can be expressed by the second order homogeneous difference equation M of n plus 2 equals mn plus 1 plus 3 mn all over 4. And they also kindly explain that these two numbers that we've met above, 200 kg and 245 kg, can be expressed as M0 and M1. The reason we're not seeing it starting on M1, which might seem logical from a kind of like from a real life point of view, is because actually the 0 is much nicer to work with. So we're not gonna argue about the first month being the 0, because that actually works much better for us mathematically, and that's what we've seen so far, and that's what I would expect to keep seeing. So the first thing we're being asked to do is to get M1 and M2. So we have M0 and M1, so then using the little formula they've given us, M2 is going to be M1 plus 3 over 4 M0. Okay, so I'm getting that from the actual second order difference equation they've given us here. So that means M2 is going to be 245 plus 3 over 4, 200. So that's going into our calculator, and we're figuring out that we're getting 395. And then if we want to do M3, that's going to be M2, 395, plus 3 over 4, M1, which is 245. So 395 plus 3/4 of 245. And that gives us 578.75, and these are both kg. So this is how much is extracted in each month. So M2 is the third month, M3 is the fourth month. So that's a nice straightforward little starter. Then it asks us to solve the difference equation for Mn in terms of n. So what we want to do here is follow through our step-by-step process. Notice how in this higher level question, we weren't given any kind of hints. In the ordinary level question, they actually gave us the quadratic. And then the first question was to solve it and to solve the quadratic. And then the third part was to solve the difference equation. Here we're being asked to do it all in one. So we'll go back to our steps. The first step is to create our characteristic quadratic equation, which becomes x squared equals, watch where your equals is in your where it is in relation to your terms, because it's not always going to be at the end. So we've x squared, then comes the equals, then x plus 3 over 4, and that's my constant. It will be much easier if we multiply out and get rid of that 4. And then you want to always have your quadratic equal to 0 to solve it. Okay, so that's kind of our basics. So now we have a slightly more challenging quadratic. You can see how they've kind of upped the difficulty by giving us one that's kind of maybe slightly harder to solve. So we're going to do a little bit of trial and error. You can use guide number, you can use your minus b formula, whatever you want. I think if we put our 2x here and here, we'll do a minus 3 here and a plus 1 here. So what that does, it gives us our plus 2 here, and it gives us our minus 6 here, and that gives us our minus 4x. That's just a bit of trial and error. Not always the most efficient way, but if that's the way you've learned it, great. If not, like I said, guide number or minus b, absolutely perfect. So we get our two answers. So x equals minus a half. So sorry, this is step 2. This is my solving. X equals minus a half, and x equals 3 over 2. So these are our two roots. They are different. So we have alpha and we have beta. So step 3 is then to use our theorem. So our theorem is Tn is equal to L alpha to the power of n plus M beta to the power of n. So we are dealing with m in this case. So it's going to be L alpha is minus a half to the power of n plus m, and beta is 3 over 2 to the power of n. You may prefer to work with decimals here, and that is absolutely perfect. If you want to work with fractions, that's also perfect. Whichever works best for you. So this is the decimal version, and you'll work it through. So this is what I meant by the numbers are going to be a little bit more awkward in a higher level question compared to the ordinary level question. So now we're going to do some substitution using our M0 and our M1, and we're going to solve this simultaneous equation. So I've just cleared off the screen so we have a bit more space to work. I'm going to work with the fraction version of this. If you want to work with the decimal, it should work out exactly the same. I prefer to work in fractions. I think it does make my life a little bit easier, but it's completely personal preference. It is good to note how we're using two different m's here. We have n on this side, and then we have an m over here. And this highlights a really important skill for us, that in maths and applied maths, how uppercase and lowercase letters can mean different things and can appear together. It's rare, but they can. So it's really important that you are able to distinguish between your own letters. So for me, I try to use this kind of a more angular M for my capital versus a more curved one for my lowercase. Majority of the letters you can do something like that. Some of them are tough, like C, you have to really make one bigger, one smaller, but just to bear that in mind. Okay, so we're going to work with the two bits of information we were given. I just pulled them onto the top of the screen so we have it. So we're going to use M0 first. So we have minus a half power of 0 plus 3 over 2 power of 0. And when I do that, I should get 200. So that gives me L plus M equals 200. So that's lovely and straightforward. I'm going to call that equation 1. And then if I work with M1, I have L minus a half to the power of 1 plus M 3 over 2 to the power of 1, and that equals 245. So what that gives us is minus L over 2 plus 3M over 2, and that equals 245. The reason I prefer working with fractions is because at this point, I now know that actually simply by multiplying across by 2, I'm going to end up with an equation that doesn't have any fractions in it, which makes life so much easier. That can be harder to see with decimal. So we get minus L plus 3M, and that gives us 490, and that's equation 2. So we're going to work equation 1 and 2 together. L plus M equals 200, minus L plus 3M equals 490. L's go, 4M equals 690, M equals 1. So we get 1, 7, and then 1 over 2.5. So not a lovely number, but this is what we're expecting at higher level. So then if I go back to equation 1, L plus 172.5 is equal to 200. So we can figure out L then by subtracting them. So that gives us 27.5. So our final answer is MN. I said one thing earlier and I do the opposite, so trying to keep that M quite angular. So my MN, L is 27.5 minus a half to the power of N plus 172.5, 3 over 2 to the power of N. And that has gotten us the answer to our second order homogeneous difference equation. So now that we have our Mn in terms of just N, we're going to look at the last question, which is calculate the total mass of opal that is predicted to be removed during the first 6 months. Now, often I get the question like, is there a shortcut for this? What I'd say is because there's 2 parts, we don't have a shortcut. If there was only one part, so if, for example, we only had like this bit here, and then it would be a geometric sequence and we could turn it into geometric series and then we could use our shortcuts. But this is effectively a combination of both. So you'd have to work with both pieces individually, which you could, but really it is just going to be quicker to work them out by hand and then add them together. What did catch students out here is just this 6 months. Be careful because our first month is actually M0. So we have M0 is 200, we have M1 is 245, we have M2, which we worked out in part 1 as 395, we have M3, which we worked out as 578.75. You can use your formula from part 2, or you can literally just go back to the original difference equation to work out M4 and M5, because that is 6 months. So if you look at them, that is 6 months. We're starting at 0. So including M6 will be incorrect. So working at M4 will be 875. Working at M5 works out about 1309. It's 0.0625. So we'll add that in for accuracy. So then the total of the 6 months, adding all those together, we get 3,602 and 8125, and that is the total amount of opal that we predict will be removed in the first 6 months. So even if you couldn't do part 2, you could still do part 3, and that's important because often if you get stuck or if you think something's gone wrong in your solving, and then you kind of give up the question, it is possible to keep going. So don't always think that there is a dependency. Obviously we can use the answer from the previous part, and that's absolutely valid, but it's just as accurate to use the difference equation, especially given that we're working with consecutive months here.